In this video, I'd like to discuss refraction of light. We know that light travels in transparent media such as air, water, glass, plastics, and so on and so forth. However, those materials are not optically the same. Their optical properties are different. More specifically, one optical property, which is called optical density, is different for those materials. And because of that, if light rays pass from one material into another, the direction of travel changes. And that effect, or that phenomenon, is known as refraction. So, to quickly illustrate the concept, let's consider two different materials in contact with each other. So we have glass and we have air. Let's have a single light ray incident from the air upon the glass. What will happen is the light ray will change direction once it transitions from air into glass. So if I draw an imaginary line which is perpendicular to the surface of the glass, which I'm going to call normal to the surface. So again, this is an imaginary line, it doesn't really exist. And I continue this line into the glass. Then the light ray, after entering the glass, will bend towards the normal. So the direction of travel changes. And this is due, again, to the fact that air and glass have different optic properties. Glass is optically more dense than air. The optic property that determines how light bends when it transitions from one material into another is called index of refraction. Let's discuss this property. So the index of refraction is labeled with the letter N, and as the name suggests, this is just a number. And it does not have units. The index of refraction for water is equal to 1.33. The index of refraction for glass is, so depending on the glass, it can vary from 1.5 to 1.9. The most common one used for solving various problems is 1.5. So unless otherwise specified, we'll use this value. And then the index of refraction of air is the same, or it's extremely close to that for vacuum, so we use the same value for both. So the index of refraction of air or vacuum is going to be 1. So the larger the index of refraction, the more the light entering that medium is going to change direction of propagation. The more the light entering the medium will change direction of propagation. If we look at the refraction of light incident upon water on the left here versus glass on the right here, coming from air, we see that the light bends differently when it enters those two substances. So when the light enters from air into water, it bends less towards the normal, changes direction less, compared to when the light enters from air into glass. And the reason for the different amount of change of direction of propagation is that the index of refraction for those two substances are different. So the larger the index of refraction, the more the light ray will change direction of motion when it enters the other substance. What is the relationship between the index of refraction for each medium as the light propagates and the angles of incidence and the angle of refraction? This relationship is given by Snell's law. So let's discuss it. Let's discuss the general propagation of light between two different media without specifying the medium themselves. So we have medium 1 and medium 2, and light will be incident from medium 1 upon medium 2. So since those are two different media, each of them will have its own index of refraction. Let's call the index of refraction of medium 1 and 1, and the index of refraction of medium 2 and 2. Let's look at one ray coming in from medium 1 into medium 2. So in medium 1, this is called an incident ray, and then in medium 2, that will be the refracted ray. So I'm going to measure the angles of incidence and refraction with respect to the normal to the surface at the point where the incident ray enters medium 2. So the angle that the incident ray makes with the normal, we are going to name angle of incidence. So theta I is the angle of incidence. And then the angle that the refracted ray makes with the normal, theta sub r, we are going to call the angle of refraction. So theta r is the angle of refraction. So what is the relationship between the index of refraction of medium 1, the angle of incidence, the index of refraction of medium 2, and the angle of refraction? This is given by Snell's law. Snell's law states that the product of the index of refraction of medium 1 times the sine of the angle of incidence is equal to the product of the index of refraction of medium 2 times the sine of the angle of refraction. And so the sine function is a function that's available with any scientific calculator. And so you can calculate sine of any angle as long as this angle is converted into degrees. So you must set your calculators to calculate in degrees. And given 3 of those 4 quantities, you can calculate the 4th one. So Snell's law allows us to calculate either the angle of incidence or the angle of refraction, or either of the two indices of refraction, as long as we know the other 3. Here's an interesting question regarding refraction of light. What happens to the direction of travel of a light ray when it transitions from air into glass and then back into air? So we already know what happens during the transition from one medium into another, from air into glass. The incident light ray is going to change direction of propagation, so it's going to bend towards the normal, which is here. But now we need to figure out what's going to happen when the light ray exits the glass and enters the air again. So I draw another normal at the interface between the glass and the air after that. And now the index of refraction of glass is larger than the index of refraction of air. And so that means, actually let's put the values here just for reference. And glass is equal to 1.5 on average, and air is equal to 1. So the index of refraction of glass is bigger than the index of refraction of air, and so that means that the light ray will bend away from the normal when it passes from glass to air. And so it will look like so. And it turns out that the incident ray from air onto glass is parallel to the refracted ray from glass into air again. There is only a shift due to the fact that light propagates in a different direction in the glass when it comes from air. So here is a set of 4 images of light from a laser source incident upon a piece of glass or a glass plate, and showing how the light refracts as it enters from air into glass. So when the light is perpendicular, direction of incidence is perpendicular to the glass plate, there is no refraction, and that is because the angle of incidence is 0. When the light is incident upon the glass at a certain angle that is not 0, then it refracts in the glass, so it bends towards the normal. You can see the direction of propagation here and here is slightly different. As I increase the angle of incidence, that will also increase the angle of refraction inside the glass. Still, the direction of propagation is, or the angle of refraction is smaller than the angle of incidence. The light bends towards the normal. But now you can also see how the light exiting the glass plate, the ray here is parallel to the incident ray, except it is shifted a little bit. And as I increase the angle of incidence even more, then it's even more obvious that the light bends towards the normal inside the glass, and then when it exits the glass, the 2 rays are parallel to each other. So a question can be asked, why is the light changing direction of propagation when it enters a different medium? And the answer to that question is that the speed of propagation changes. So light has different speeds in different materials. The fastest speed is the speed in vacuum, which is 3 times 10 to the 8th meters per second. And then in denser material such as glass or water or plastic, the speed is slower. And due to that slowdown, the light rays bend towards the normal at the surface of incidence.